Hello everybody, welcome to my class. My name is Brandon Pham, and today I'll be talking about intrinsic rate of increase, carrying capacity, density dependence, and how it influences population growth, examples and outcomes of two studies done on density dependence, oscillating dynamics, how might oscillating dynamics contribute to stable species coexistence, Petersell's hypothesis and concept of storage effect, and explain Cheston and Warner's 1981 mathematical model, which further expanded on Petersell's ideas. Now, first, to begin with, what is an intrinsic rate of increase? An intrinsic rate of increase refers to the population size that can grow under unlimited amount of resources. So therefore, they end up growing exponentially because there's no cap on the amount of resources that the population and the environment can sustain. So therefore, there's no roof, and the exponential amount of growth on a population is infinite. So this only refers to the per capita birth rate and the per capita death rate. Therefore, the equation for an intrinsic rate of increase is per capita birth rate minus the per capita death rate. Now, there's such thing as a carrying capacity, and this is in every single environment because resources are not unlimited. So when the resources are limited, the environment has a threshold where they can no longer sustain past the amount of infinite population growth that can possibly happen. So what ends up happening is the population grows exponentially, and then it reaches this threshold where the environment can no longer sustain population above that. So the population levels off at the carrying capacity area because there's a decline in the amount of resources that are available. So the population also starts dying off, and they end up equaling out where it's just where the equilibrium is in the carrying capacity. So then birth rate equals death rate around that area where the curve starts to level off. And eventually it could decline and then come back up again. But no matter what, there's a carrying capacity that the environment can hold. Now, let's talk about density dependence and how it can influence the population growth. Well, density dependence refers to factors where the effects on size and growth of a population vary with the density of the population itself. So these density factors can be depletion of resources, accumulation of waste products, aggression between individuals, which causes competition between them and mating opportunities. And all these are negative feedback inputs that are put in between population size and the per capita growth rate. So this is a representation of what density dependence looks like. Now, when density is low, that allows plenty of resources for individuals to give birth, and the individual rate necessarily declines because there's enough resources for them to sustain themselves, and then so birth rate equals more than death rate. But now, whenever the density is high, there's a lot of individuals, so the resources are limited, and now there's competition for those resources, so it ends up being competition and individuals die. Now, two examples of studies shown on density dependence would be Roy Wood and Hansky in 1992, who analyzed 6,000 times a series of aphid and moth population and recorded at various sites in Britain. So what they found was density dependence of 69% for aphid and 29% of moth. But when they removed the short-term series, which was less than 20 years, in the analysis, it showed that there was a significant amount of density dependence, which increased from 69% on aphid to 84%, and then from 29% of moth to 57% of moth. And another study done by Turchin and Taylor in 2006 found that density dependence in 18 of 19 forest insect populations and 19 of 22 vertebrate populations. Therefore, density dependence is very prevalent inside environments. Oscillating dynamic refers to two species fluctuating at one given time, and it refers to the variable environments that alter over a series and seasons, such as times like weeks and years, which ends up causing a benefit at one point in time for both species. And they reach sort of like a knot where the frequency is fluctuating between 0 and 1. Now, just because there's a benefit at one point, it does not mean that at the next one, it's going to be at the same point and it's due to the same alteration, because environments are always changing and the conditions are different. So when they reach this stable coexistence, there's a different reason why. So let's talk about what a stable coexistence is first, before we can finally say like why oscillating dynamics could lead to stable coexistence. Now, stable coexistence refers to the species' tendency to recover from low densities, and that species' density may fluctuate over time, so they don't disappear. So if we're looking at a frequency in the environment, this is a great example of an oscillating dynamic. We have species A, which is starting higher with the population, and species B, which is starting lower. And eventually they end up meeting at one point because there's a stable part where the benefit for both in the variable environment is met here. And then it ends up benefiting species B more, while species A is declining, and it's giving time for it to recover from its low density, and then it comes back again and they meet at the same point. So this is how the oscillating dynamics can lead to stable species coexistence, because the species is not hitting zero. It's fluctuating in between 0 and 1, and so it gives them time to recover and eventually hit back at the point. So now let's talk about Sell's hypothesis and his concept of the storage effect. Now, Sell's hypothesis is as temporal variation in recruitment could allow coexistence of many species of fish competing for territories on a coral reef. Now, some background information. Sell predicted that since coral reef has immense amount of competition for space and territory, which leads to biological diversity being very high, and he observed that coral reef, once they obtained and held their organism, it held that organism until that organism died. So that's why when he talks about temporal variation in the recruitment, this recruitment refers to how that reef can maintain and hold that new species of fish fry that comes through. Now, some observations and notes that he said. He said that even if fish have generalized diets and habitat usage, or as long as there's temporal variation in availability of territories and death of organisms, and variation in settlement of fish fry, of different fish species on those territories, there will be a wide diversity of species that can coexist within the coral reef, because some species might benefit more whenever the time is cold, and then whenever heat is much more, then that species that was cold can decline, and then the species that are with the heat can exist much better. And then there's a variety of species that are coming in and out of that coral reef. If one ceases to exist, another one replaces it right away. So that's why he ended up turning the thing in 1977 that random nature of unpredictableness in the supply of space leads to an interspecific competition for space, like a lottery, because it's like a first come, first serve. Once a species dies, another species comes in to take over. And there's no species that can consistently win because there's such a changing environment that's so dynamic. So the high diversity may be maintained because of unpredictable environment, and it prevents development of an equilibrium community. Now, there's also such thing as a storage effect. The storage effect says that there's temporal variations in environment conditions which lead to species coexistence even in stable environments. Now, what Sells noted was that temporal variation in long-living adult fry that can store the population contribution allows for a temporal fluctuation to a stability mechanism. So, some species that die off due to the simple and temporal variation in the environment, there's also long-term variation from the fries that can hold the population longer. So this is technically like an oscillating dynamic. Now let's talk about Adler. Adler used the storage effect idea and applied it to prairie plants in Kansas. Now these prairie plants had grass species that made over 95% of the vegetative cover. He took into consideration 3 species that had a long lifespan. Each had different abilities that is favorable to a certain condition that it was in the environment. The variation in the environment that changed was favorable to one species over the other. But what he noticed was that during the good years, there was an increased amount of competition. And whenever there was the bad years that were detrimental to the 3 species, there would be neighboring species that were nearby. They had a weak amount of competition, and sometimes they facilitated the strong species. Now, Chesson and Warner's 1981 mathematical model helped generate Sell's idea with the mathematical model, which they termed the lottery model, since the territory's establishment is on a first come, first served basis. Now, the dynamic fluctuation in species composition is what allowed for all this to happen. So what ended up happening was you start out with the original distribution, and then about 10% of the adult population dies. So now there's open slots for 1 or 2 to take infill for this. So species 1 and 2 reproduce, making a widely dispersed amount of larvae, and then what ends up happening is a dynamic fluctuation in species composition, which is absolutely random. So you have one where there's a lot of 2s and some 1, and the other one where there's a lot of 1s and no 2s. So there are some key features of the lottery model. specifically that adult fish hold territory on reef until death, which I've already stated. As you can see, 1, 2, 1, 1, this pattern. They still are here and they haven't died, so they're holding it. And that they reproduce more than once, so there's some overlapping species, which you can see in this here. And that necessarily territories are necessary for survival and reproduction. So there's more fish attempting to establish territories than there are territories, which is why allocation is first come, first serve. Whichever slot fills in first is the population that'll get there. And that fries are produced in abundance and are dispersed, and that the fry survival depends on the environmental condition. So one condition might be better than the other for one, whereas the other condition can be better for two. But that's about it. So these are the topics that I covered, and I hope that you all learned something very special today. Thank you.